So how can we relate these elementary steps to something that would go into a rate law? So as we talked about in the previous chapter, we can't look at a complex reaction, just given a reaction equation, and know what the rate law will be for it. Because the reason why is that we don't know the mechanism. We don't know what specific steps it go through, what things have to collide with each other, what concentrations matter to be able to figure out what the rate law is. So we have to measure the rate law through changing concentration and measuring how the rate changes. This is unlike for complex reactions. If we know a reaction mechanism, we can write a rate for any step involving a reaction from an elementary step, because we know exactly what's happening and what concentrations matter. And so we can write a rate law for each of these types of steps that we talked about in the last video. So if we have a unimolecular reaction, the rate just depends on how much A there is. If there's no A, the rate is 0, and it'll go faster the more A there is, because A is going directly to products. And so if we want to write a rate law that goes with each of these types of steps, we can say, okay, for a unimolecular reaction, the rate, we'll call V, is just equal to some rate constant times the concentration of A. So there's a direct one-to-one correspondence here that we have A going to products, and this is an elementary step, so we can say the rate law for this step, not for whatever whole reaction this involves, the rate law for the step is this. And similarly for a bimolecular reaction, it depends how much of A and how much of B we have, and so the rate law for a bimolecular reaction is just going to be whatever rate constant goes with that elementary step times the concentration of A times the concentration of B. So the rate is directly proportional to their concentrations because they both need to be present to collide. And so if we have more A and B, the rate will go faster. If we only have more of A but not more of B, it'll go a little bit faster but not as much. Same thing for the other way around. For a termolecular reaction, we have the exact same thing, but now we have three things that need to collide, and so it depends on all three of those things. So our rate will be equal to the concentration of A times the concentration of B times the concentration of C. So that allows us to determine from a mechanism perspective, for each step of the reaction we can figure out the rate. And that is what makes this useful, of determining a mechanism and being able to relate that to a rate law. Now often, unless there's only one elementary step, if there's one elementary step, it's pretty straightforward to write the rate law for the complex reaction. It's just equal to the rate law for that step. But if we have something that's more complicated, which we usually do, where there are multiple steps involved, we will go over some techniques for taking this idea of, if we know the elementary steps, we can write the rates for those steps, and taking what we know about the mechanism and turning that into a rate equation, right? A rate law that we can describe for the complex reaction. But we have some more things to cover before we get to that point.